Hello everyone, I am Abhishek Bidre.
And I am Prajakta Dalwai. Today, we are here to present our research on adaptive on-device small language models for industrial maintenance assistance with generative fault scenario synthesis. Well, moving forward with our presentation, we shall discuss the problem, prior work and the research gap, system design and the methodology, and come to our results while discussing our discussions and limitations with the conclusion. Ladies and gentlemen, we all use Google one way or the around, though we are experts in our own domain. Now imagine you're completely on a deserted site or defense restricted manufacturing site surrounded by deep ocean. Your industrial equipment fails and you're completely in the air gapped or low connectivity restricted sites. Now here your cloud AI is unavailable. You have to go through the manual OEM documentation search which causes you delay by minutes. And you know that in a production or a manufacturing system, every delay costs you a penny. Well, me and my teammate have always been fascinated by how Edge AI works. So thus we were brainstorming on the use cases of Edge AI, and we noticed that the current research either uses cloud AI or it depends upon the external LLMs that for the inference that need connectivity somewhere or the around. Even if one could run a local model locally, they still face the issue of data scarcity. And that's when we asked ourselves this small question that can a small language model be compressed to run on a cheap single board computer, that is a Raspberry Pi, deliver diagnostic guidance that is faster, safe, and more useful than the manual documentation search? And can't it just generalize across completely different classes of industrial equipments? That we started our research, and from the base papers, we noticed that all the papers either had one aspect but didn't include others. For example, the cloud maintenance LLM had exact industrial maintenance AI and local, but it didn't have any edge deployment. It was not fully offline operational. It didn't have multi-equipment valuation, and it wasn't uncertainty aware escalation. The next base paper, Edge SLM benchmarking, it did have edge deployment, but and fully offline operation, but it lacked for the use case of industrial maintenance AI. It lacked the multi-equipment evaluation and the uncertainty of escalation. Similarly, the next paper that is on device RAG libraries gave us the edge deployment at the local RAG, was indeed fully offline operational, and gave us the libraries that helped us understand how system could be built and designed. In the next paper, that is the PI plus LLM anomaly detection, showed us the research gap that yes, there are aspects, but they are implemented in segments and not completely into the one system. So thus we decided to build answering the previous question that I had mentioned while covering all these gaps in one. That is industrial maintenance AI, as deployment, local RAG, full offline operation, multi-equipment evaluation, and uncertainty aware escalation. Now, with the research gaps in our mind, we decided to have four research objectives and lead our contributions. The first one was to establish a four-stage offline diagnostic pipeline within a strict 4 GB RAM ceiling. Next was to eliminate the manual search latency that is from 20 to 40 seconds down to just few seconds. Our third objective was to resolve the industrial data scarcity via on-device few short generative synthesis. And lastly, our edge deployment evaluation, that is implement a deterministic entropy-based safety gate for the exploit. Now, all these contributions, our methodology, our system design shall be discussed in the further presentation.
Now, addressing the above mentioned objectives and to test our hypothesis, we engineered a fully offline four-stage diagnostic pipeline designed to operate under a strict 4 GB memory ceiling on a Raspberry Pi. Four distinct stages here are the input synthesis, local RAG retrieval, INT for quantized inference, and the entropy safety gate. In the first stage, we ingest the operator's query, build a live modus TCP telemetry, register snapshot, and prepare the RAG context. In the next stage, that is stage 2, query is encoded using a lightweight 22 MB all mini LM model. We search a local ChromaDB vector store containing the pre-indexed OEM manuals. Through a grid search optimization, we set a cosine similarity threshold that is of delta of 0.62 and retrieve only the top K3 matching chunks. This grounds our model in the exact technical manual instructions only. Whereas in the stage 3, the combined prompt is passed to an IND4 quantized 5-3 mini model running via the highly optimized llama.ctpp runtime. Ensure our system can deploy on standard, low-cost industrial ports. We enforce a strict 4 GB logical memory using the Linux C groups. We split our RAM explicitly where 512 MB is for the OS, 1024 MB is for the KV cache to support long context, and 2450 MB for the model weights. As you can see below that how the peak RAM, time, and accuracy are affected. Well, in the stage 4, it's a simple yes or no question here. That is, if the entropy exceeds the calibrated threshold of tau is equals to 0.45, the output is immediately aborted and routed to a mandatory human technician. Hence, the output below the 0.45 threshold are released and to an autonomous repair advice. This state is deterministic and not advisory at all. Also, we measure the output uncertainty using the normalized word frequency entropy proxy, avoiding the memory cost of tracking logics across 30,000 token vocabulary on the ARM CPU. Okay, so now that we are past the methodology, ladies and gentlemen, the next important concern is that if the dataset used is correct and verified, does this hypothesis and the architecture work as promised? How did we evaluate the system, right? The one major roadblock in our research was the absolute scarcity of open source industrial maintenance benchmarks. We couldn't rigorously evaluate our architecture without data. So we leveraged our on-device model to synthesize completely new dataset via FibShort prompting, starting from just the 50 seed queries to ensure the integrity of our evaluation. To ensure it, I manually cross-checked every single generated scenario against the OEM manuals to ensure the validity. This resulted in our industrial maintenance QA of 600 benchmark, that is highly diverse 600 triple evaluation set covering pumps, chillers, and CNC machining centers, where 240 triples were for the for the CM pump, 180 for the carrier chiller, and 180 for the CNC machining center. Also to mention that this is the first multi-equipment edge AI benchmark of its kind, allowing us to evaluate cross-domain generalization without any equipment-specific fine-tuning. When we ran the evaluations, the results were incredibly validating. The key result here is the engineering trade-off. INT4 reduces the model's RAM footprint by 64% from a 6.74 GB to just 2.41 GB while delivering 3.7x higher throughput. Importantly, this comes at a relatively small accuracy cost. The accuracy drops only by 3 percentage points from 96.1 percentage to 93.1 percentage. At the same time, the mean time to first token falls to just 2.4 seconds. So rather than optimizing purely for maximum accuracy, IND4 gives us a much more practical balance for accuracy memory usage and responsiveness for the constrained edge hardware for the constrained edge hardware. Well, the next question was whether the accuracy was actually coming from our retrieval pipeline. So we performed a strict ablation study. Without retrieval, the INT4 model achieved only 71.3% response accuracy. After adding a local DB based RAG, accuracy increased to 93.1%, a 21.8 percentage point improvement. This shows that the quantized model alone is not responsible for the final performance. The local RAG layer provides the domain specific knowledge needed to make the system effective for industrial maintenance. Furthermore, look at per equipment breakdown. The CM pump leads with a 94% accuracy, while the carrier chiller and the CNC centers perform incredibly well at 92.7 accuracy. This proves that a single unified local RAG index can generalize across vastly different machineries, terminologies, and alarm codes without any expensive equipment specific fine tuning. Well, Gate successfully escalated 88% of advisory prompts, which are designed to induce the harmful or the hallucinated outputs. However, the gate missed 12% of these prompts. When we analyzed the six false negative, where five of them involved cases where the RAG module retrieved a highly structured plausible passage with a cosine similarity above 0.75. This retrieved structure allowed the model to generate a highly fluent, low repetition response that was contextually wrong but had very low word frequency entropy. To resolve this, our highest priority is next step is replacing simple word frequency proxy with the SESC structural entropy measure, which evaluates the true uncertainty of the model's internal representation. Additionally, our current evaluation loop is closed since the benchmark was generated by the same model family. We are actively planning independent trials with practicing maintenance engineers to gain human grounded feedback. Finally, we want to transition from simulated telemetry to the live modus TCP registers and explore the local LoRa fine-tuning directly on the edge hardware. Well, ladies and gentlemen, thank you, respected reviewers, for watching our presentation till now. So in the conclusion, we set to answer this one simple question. Can we replace the 20 to 40-minute manual paper documentation search with the fast, secure edge native AI assistant and just a cheap $35 code? The answer is indeed clear and a definitive yes. Our system achieves 93.1% overall accuracy with rapid 2.4-second response time, operating entirely with a 3.41 GB RAM footprint on a Raspberry Pi with zero connectivity. 88% of the advisory prompts escalated to a technician. The results demonstrate that the practical on-device maintenance assistance is feasible. Though Safe Edge AI is viable today, we open the door for the modern responsive maintenance in the air gap plans, secure manufacturing networks, and remote installations worldwide. We don't have to wait for the cloud to be secure, as on-device intelligence is already here. With that, we complete our presentation here. Thank you for this opportunity. Thank you for your time and the honor for us to present our table. Have a phenomenal day ahead, everyone. Thank you.